Everyone, how was your meal? I hope you enjoyed it. And talking about enjoying stuff, I have the luck to share a space with Hugh Brown. Did you get it? Sharing a space? And okay, I know it was a bad joke, but this talk is going to be as interesting as all the others, but we are now taking the limits to another level. So, Hugh, welcome to this talk. What can we expect about it?
Thank you for giving me the chance to talk here. So the talk's going to be about Polaris. It's an open source project to apply machine learning and data science techniques to satellite telemetry. Our hope is to give satellite operators a way to explore the relationships in their telemetry, the information about their satellite to help them operate it better.
Interesting. And talking about the space, as you know, there have been a lot of news about what is going on right now. So I believe everyone should be interested on this because it will be a milestone for humankind. So just to wrap up and begin with the talk, just tell me, Hugh, where are you located right now? Are you in on Earth or are you in space? Where are you right now?
Sadly, I have not yet made it to space, although my goal is to get there. I'm in New Westminster, British Columbia in Canada, one of the suburbs of Vancouver. So I would have been attending PyCascades in person if that had worked out this year.
Awesome. So, everyone, fasten your seatbelt because now we are aiming to the stars and let's watch our talk.
Hi everyone, my name is Hugh Brown, and thank you for watching my talk on Polaris, open source machine learning for spacecraft operations. I'm sorry we can't be having this chat in person, but I'm really grateful to the organizers of the PyCascades conference for allowing me to record this and share it with you. I hope you'll like it. I'm going to be talking to you today about satellites and the analysis that we can do on the telemetry that we get back from them. I'm going to be talking about a special kind of satellite called a Cubesat, much smaller than the sort you're probably thinking of. I'm going to be talking a little bit about telemetry and what it is, the information a satellite sends back down to Earth about the satellite. I'm going to be showing you Polaris, explaining how it works, and giving an example of the analysis that we can do for a satellite called LightSail 2. And I'm going to be talking about the future of Polaris and inviting you to join us as we build this tool. Before we get started, a little bit about me. I am a Linux sysadmin and have been for almost 20 years now. And over that time, a lot of my work has been shifting from the operational side of things, poking at servers, to software development. And Python has been a big part of that, whether I'm tool building or helping to write and operate the cloud services that I'm responsible for. Python is a fun tool. It's got a wonderful set of libraries that I can use. It's a really great and welcoming community, and it's just been a really, really good fit. I'm an enormous fan of open source and free software. I am where I am because other people have been generous enough to share the tools that they built and the knowledge that they learned as they did so. And I want to find a way to pay that forward. I'm an enormous space nerd. You can see by the things on my wall and on my desk that I'm pretty excited about space. I can talk to you about how many astronauts are on the International Space Station. I can tell you my favorite Apollo mission. I follow along with the missions that humanity sends to explore the planets and the stars. And I'm really fortunate that Polaris lets me combine all of that, and I'm happy to be sharing it with you. Now, if you're thinking about a satellite, you're probably thinking about one of the sorts that you see here. On the left is a communication satellite, KoreaSat 7, which is providing, as you might guess, communications for Korea. In the middle is a space observatory called Planck. It was launched by the European Space Agency to study the remnants of the Big Bang, to learn the past, the origin, and the future of our universe. On the right, you can see a weather satellite called GOES-16, and it, as you might expect, takes measurements and photographs all the time, beams them back down to Earth so that forecasters can make better weather forecasts and so that we can follow along with climate change and global warming. Now, these satellites are large. Sometimes it's not obvious. You can see the people for scale there, which is why I picked these photos. But also, they're really, really expensive. And the result of that is that they don't benefit from the same economies of scale that allow, for example, your phone to be more capable and cheaper every year. Kind of a vicious circle. The satellites are big, and that makes them expensive. They're expensive, so you don't want to take any chances. You don't take any chances, so you make one or two of them. And you don't get the benefits of making millions of them. Now, Cubesats, on the other hand, turn all of that on their head. You can see a picture of one there being held in someone's hand, and this is a model of one. It's 10 centimeters by 10 centimeters by 10 centimeters. That's one unit. A 2U satellite, a 2U CubeSat would be 20 centimeters by 10 by 10, and a 3U or 3-unit satellite would be about the size of a loaf of bread. You can see some of those 3U CubeSats in the middle. Those belong to a company called Planet Labs. Now, there are lots of different missions being sent up by CubeSats, but Planet Lab have taken this kind of to the next level. They operate hundreds of these things. Now, each one lasts for maybe just a few years, but they only cost on the order of tens of thousands of dollars to build instead of hundreds of millions of dollars to build. And because they operate hundreds of these things in orbit, they are able to take images of the entirety of the Earth's surface each and every day. And on the right, you could see a couple of CubeSats called Marco and Polo that were built by NASA. They accompanied a mission called InSight, which went to the planet Mars. Marco and Polo were along to act as communication relays as an experiment to see if CubeSats could work in orbit around a different planet, and turns out they can. Now, I mentioned how inexpensive these things are to manufacture, and in fact, a lot of missions end up being built by the engineering departments of different universities. For a few tens of thousands of dollars, you can afford to have your undergraduates assemble one of these in order to do a technology demonstration or a scientific experiment. One other way that it ends up saving money is with launch. Now, the larger something is, the more massive it is, the more it costs to send up to space. But also, the larger something is, the more volume it has, the more expensive it is. The top left-hand picture you see there is a CubeSat being put into a deployer. That's the metal sleeve you see. And down at the bottom, underneath that great big expensive satellite, which is paying for the whole launch, is our deployer attached to the very corner of the rocket. And once the satellite, the main one, gets deployed in its orbit, the other one will be sort of kicked off and left to find its own way. On the right, you can see a picture of a couple satellites being deployed from the International Space Station. These are actually kicked out in an airlock. Not kicked, but you get the point. And they would have gone up to the International Space Station with supplies for the astronauts and other things. The end result is that you have something that is not very expensive to manufacture, a lot cheaper to launch, and because you can literally tuck these things in corners of existing launches, there are a lot more opportunities to launch. That allows these satellite operators to benefit from the sort of scale that cloud service operators are familiar with, where you can scale out instead of up. You can make a bunch of things that are perhaps less capable rather than one very expensive, very capable thing. Now, at this point, I've got to start talking about telemetry in order to understand Polaris. Telemetry is the information sent back by a satellite about the satellite and its components. And this is the sort of information that you need as an operator in order to understand the state of your spacecraft, whether it's happy or sad, doing its job, in trouble. This is a dashboard set up for a mission called Bobcat 1. Now, it's one of the university experiments I mentioned. It was launched from the International Space Station in November of 2020, and it was built by Ohio University. And here you can see the sort of information that the satellite is sending back down to Earth. It's sending battery input and output power, battery voltage, solar panel input current and power, even how much space is left on its flash storage. And with this, satellite operators can understand how well things are going and decide what might need to happen before they take another action, like continuing with their experiment. Now, the information that you're seeing here is collected by a very special group of volunteers, a wonderful project called SatNogs. SatNogs is a network of collaboratively scheduled satellite ground stations run by volunteers all over the world, more than 200 of them. Every dot you see here is another satellite ground station run by ordinary people. The reference architecture for a SatNogs ground station is pretty modest. A Raspberry Pi, a $25 software-defined radio. But with this, the ground station operators can capture radio broadcasts from satellites passing overhead. And if the operators have published the specifications for their telemetry, they can decode that into ones and zeros, and from there into things like voltage and temperature readings. And this is where Polaris comes in. We are an open source Python tool for exploring and analyzing satellite telemetry obtained from the SatNogs network. We aim to provide satellite operators another tool to explore that telemetry and to find connections that they might not have seen. We're open source, published under the LGPL v3. We're a Python project, and that was an easy decision to make. There are lots and lots of tools for machine learning, for numerical computation, even for command line libraries in Python. All the things that you use on a daily basis. And like SatNogs, we are a project of the Libre Space Foundation. We are a sister project of SatNogs. And the Libre Space Foundation exists to promote open source applications for space. We're happy to be part of their organization. Polaris started in 2018, and since then we've collected more than 600 commits from 11 different developers in 5 countries. Canada, that's me, Germany, Spain, Belgium, and India. We've participated in the Google Summer of Code twice, and we hope to do so again. Polaris, at its heart, is a command line application, and a fairly straightforward one at that, even if it does some interesting things. We use the click library, and if you haven't looked at it before, I highly recommend it for all your command line needs. We have 3 subcommands: fetch, learn, and viz. Fetch brings down information from the SatNogs network and prepares it for analysis. Polaris Learn is where we apply machine learning in order to build a dependency graph, which I'll be explaining in a moment. Polaris Viz allows the operator to explore that dependency graph, the result of the analysis that we have done, to manipulate it, to explore it, to find connections that they might not have otherwise found. Let's get into it in a little bit more detail. Polaris Fetch takes as its arguments 2 things, a satellite name and a time range. And with this, it goes off to the SatNogs database in order to find all the telemetry that SatNogs has collected from volunteer ground stations for that particular satellite. And just to mention again what I said before, we depend on satellite operators to publish the specifications for their telemetry. Often university and scientific research places will do that, but of course commercial operators like Planet Labs will keep that sort of thing to themselves. We also, though, fetch 2 other sources of information. And I'm going to just mention that this is the work of our Google Summer of Code student from last year, Aditya Venkateswaran. He built a library called Venn-Vili-Vanilli, which allows us to fetch 2 different things. One is orbital information. We want to know where a satellite was at a particular time. Was it in shadow or was it in bright sunlight? Was it close to the Earth's magnetic poles? The other thing that Venn-Vili-Vanilli fetches is space weather data. In fact, Venn-Vili-Vanilli is the Tamil word for space weather. And if you haven't come across space weather before, it might sound a bit odd, but it's true. There is weather in space, even if there is no atmosphere. It happens because of the interaction between the sun's magnetic field and the Earth's magnetic field. Now, on the ground, we experience this as the northern lights or the southern lights. In space, there are a couple different effects. One can be changing levels of radiation, which can have knock-on effects on onboard computers on the satellite. Another effect is to sometimes raise the height of the atmosphere. Even if it's quite rarefied, it can still have an effect on the orbit of a satellite and, in fact, change it in some way. And we want to include this in our analysis in order to see the effect that it has. Once the information is downloaded, it's interleaved and written out into a JSON file. And that JSON file on the operator's computer serves as the input for the next part, Polaris Learn. Polaris Learn is where we apply machine learning in order to build the dependency graph that I mentioned. We use the library XGBoost. It's very popular, very easy to get started with, and does a very good job. It works in an interesting way if you haven't come across it before. It doesn't build just one model, one way of predicting, but instead builds lots and lots of models, each of which may not be so good on its own, but combined they correct for each other's errors and make something much better than the sum of their parts. We build the dependency graph, which is a set of connections between different elements of telemetry. So on the Bobcat dashboard, I showed you how we had solar panel voltage and free disk space. The dependency graph would try to determine if there's a connection between those two, if they vary in concert with one another. If there is, we say that the weight between those two nodes of the dependency graph is quite high. And if there is a weak connection, or perhaps none at all, we say that the connection is weaker. The output of this is another JSON file, the dependency graph, which is saved again to the operator's computer. And from there, it serves as input for Polaris Viz. Polaris Viz, at its heart, is a simple web server, which serves an HTML file, which loads the JavaScript dependency graph and displays it to the user in a browser. I'll be showing you what that looks like in a moment. We use the D3 library in order to allow the user to interact with it, to rotate it, to zoom in and zoom out, and to basically get a sense of the connections that it's found. And with that, it's probably a good time to talk about the demonstration I want to show you. I'm going to be showing you the analysis for a satellite, a CubeSat, called LightSail 2. LightSail 2 was launched by the Planetary Society in 2019. Now, the Planetary Society exists to promote the wonder and the joy of the exploration of space. And with LightSail 2, they had a particular task in mind, which was to demonstrate solar sailing in a CubeSat form factor in low Earth orbit. So, you might not know it, but light has a pressure. Here on Earth, you'll never feel it. It's far too weak. In space, it's still quite weak, but over time, hours, days, weeks, months, this can make a real difference. And the sail that you see here is made of mylar. It's 10 meters on a side, 30 feet, folded up inside a 3U CubeSat. And the Planetary Society wanted to demonstrate that this was a way of allowing a small satellite to use solar sailing in order to change its orbit. It was a great demonstration mission, and we are grateful to the Planetary Society for sharing the telemetry that they captured. Now, let's go to the demo here. On our website, polarisml.space, you can see this demo. You're welcome to check it out. You can also find links to our documentation, our code, and our chat, and you're welcome to join us there. So let's go to the demo. So here we see the dependency graph unfolding before us, and we see a lot of dots and a lot of lines. The dots are the individual elements of telemetry, and we can hover over them and see them come up. We can click in on one and zoom in on it. So this is an element of telemetry called battery 6 temperature, which you can probably guess what that means. The node here can be dragged around. We can interact with this. We can see everything else reacting to it as we go. There are a few lines coming out from this that we can see, representing connections to different telemetry elements. And if I zoom out, we can see that battery 6 temp is connected to battery 3 temperature, battery 6 flags, and this one up here, which is cam 1 status, camera 1 status. We can zoom in, we can zoom out using the scroll wheel. I can left click here and I can bring this around. I can zoom out and get a better idea of the shape of this and see some quite densely connected nodes, things that seem to vary at the same time as a lot of other things, and some that are not very connected at all. In fact, there are some that we can see here that are not connected to the main body of the graph at all. Battery 6 and 7 control flags, for example. And our model has found a connection between those two items, but not to any of the rest of the items in there as well. Now this is good, but it can be a little hard to find our way around. And so I want to show the search bar up here on the left. If I type in one particular item, I can see a list pop down, narrowing down as I go. So ADCS mode, Attitude, Determination, and Control System mode. Hit enter and we'll zoom in on that and we can see its connections here. We could fly in and zoom in. Now this is good, we can see the connections here. We see, for example, it's connected to the X rate and Z rate, probably rates of rotation change. Torque Y, power current. Battery 0 temperature, perhaps battery 0 powers ADCS mode. But I wanted to show some of the connections that it has to the other elements in here, to show that this is not just one blobby sort of thing, but in fact a set of subnetworks that are connected to each other. So I see over here it's connected to torque Y power current. So let's take a look. If we type PWR, we can see all the things that mention that string in their name. On the assumption that they're probably correlated, let's hit Control Enter. And now we can see that they've changed color. I think that's going to be a little hard to see on your monitor, so I'm going to hit Control Enter again and cycle through a couple times until we get to a brighter color, like that. There we go. Now if we zoom out, let's see here, how can we zoom out? We can see the cluster of power-related items over here and a few others scattered in different places. Now, if I look for another one, bus. So the bus on a spacecraft is a central connection, routing electricity to different places. And we can see here that we've got another sort of sub-network of things, kind of connected to the power ones that we saw before, but again with their own individual items scattered in different places. So I'm going to look for battery now and we'll do the same. And that's a little hard to see, so we'll cycle through until we get a little different. And also I wanted to look at the magnetometer readings. And we'll cycle through that again till we can get to something really nice and good. And from here, what we can begin to see are the different clusters of things. We can imagine that, for example, some of the power might change with the magnetometer readings. We could imagine the bus connections changing, or the bus measurements changing with the orientation of the spacecraft. And with this, the operator can see things that seem to vary at the same time as another. And this would be a perfect time to go back to the operator and begin to explore these connections and think about interactions between components of the spacecraft that we might not have anticipated in advance. And with that, let's go back to the presentation. So I've shown you the demonstration here and how even a simple analysis can give us some real insight into a spacecraft, into a system we don't know a whole lot about. But we want to do more. We want to be able to flag anomalies in the telemetry, to find spots where the behavior changes from one regime to another. And to flag those for the operator is something that needs their attention. We want to highlight outliers and give warnings to them. We want to be able to take user feedback about the dependency graph that is generated by our model. Perhaps not everything in there is useful and some parts can be ignored. We want to fold that into the output so we can make it more useful for the operator. So to conclude, I've shown you how inexpensive Cubesats can be compared to the larger satellites that have dominated the field for a long time, and how that requires operators to take different approaches to managing things at scale. I've shown you how Polaris works and shown you that even simple analysis allows us to get insight into how a satellite behaves. And we want to improve it even more to deliver even more value to the operators. And with that, I'd like to thank you for your time and invite you to contribute. You can find us at polarisml.space. There are links below. You can see here to our chat and to our code, but you'll find it all on our website, polarisml.space. And with that, I'd like to say thank you very much for your time and have a good day.
This was impressive, Hugh. In fact, this has a lot of information that we can learn from. So before we end the talk, please give us a word of advice. What should I do first if I want to get involved in some kind of project like this that are related to the space?
The best thing to do would be to go to our website, polarisml.space. You can see information about the project, but you can also join our chat room. And we've got pointers not only to our own project, but we can give you advice about lots of other projects that are open source and space related that may be interesting to you.
Excellent. So now you know, if you want to keep discussing about this topic, which is really interesting, you can go to the Q&A room here at Benuless. Hugh will be there and you can interact with him. Now, Hugh, thank you for this talk about how machine learning can be combined with space. And let's be ready for the next talk, which title is Let's Rethink Debugging, which will be at 1:55. So thanks you and see you there.
Thanks very much.